Hello, my name is Pedro, and on this short video we're going to talk about our work on persistent memory and the rise of universal constructions. This is joint work done by Andrea Correia and Pascal Felber at the University of Neuchâtel. Persistent memory is a new technology that provides a durable media with load and store access granularity. One of the things that can be done with this technology is to build failure-resilient data structures, sometimes called persistent data structures. Now, a persistent data structure is interesting, but even more interesting is a persistent and concurrent data structure, and there are three ways to obtain one. We can make a persistent and concurrent data structure by designing it from scratch. This is very hard to do correctly and usually requires an entire paper just to describe the algorithm. Or we can take an existing lock-free data structure and apply some kind of recipe to also make it persistent. This recipe is usually simple, and there are several papers on that topic. The third option, which is the one we took, is we can take a sequential data structure and you do type annotation, wrap all the functions in lambdas, and apply it to a persistent transactional memory, sometimes called durable transactional memory. This PTM takes care of the concurrency and persistence for you, so you don't have to worry about those. All three ways allow us to have concurrent and persistent data structures. A PTM can be used to create a key-value store or database engine. Before we explain how this is done, let's take a look at how key-value stores and database engines are typically made nowadays. We would take a concurrent indexing data structure for high scalability. Now, typically this would be an LSM tree, sometimes a skip list, and on top of that, we would add two-phase locking or multi-version concurrency control to handle the concurrency access on the records. We would also need a redo log so that operations on the key-value store are resilient to failures. The redo log provides the persistence or durability. And ultimately, you would need expert developers in concurrency, durability, and databases to glue all of these together and make one key-value store. Now, this typically takes years of development, and in the end, you get a blocking key-value store. With RedoPTM, we made a database storage engine by taking a sequential data structure, instrumenting its types, and wrapping the methods in lambdas to pass them to the RedoPTM. We chose a B tree, but other data structures could be used. Although the RedoPTM itself required significant expertise in concurrency and durability, using the PTM to make a key-value store required less than 2 months of work without any expertise in concurrency or durability from the developer. The end result is a key-value store that can do dynamic, durable linearizable transactions over any annotated type. RedoDB is the world's first wait-free key-value store, has null recovery, non-abortable reads similar to multi-version concurrency control, and provides ACID transactions written in C++. Thank you for watching. If you want to learn more, please watch the longer video or read the paper. Source code to the benchmarks and the wait-free key-value store is available on GitHub.